So as part of our pre-discussion on Lewis dot structures, we need to look at electronegativity trends again. So electronegativity is defined as the ability of an atom to pull electrons towards itself. If this is a huge periodic table, we have fluorine in the upper right-hand corner, and fluorine is the most electronegative atom on the periodic table. So as you go across the row towards fluorine, the atoms become more and more electronegative. And as you go up towards fluorine, they become more and more electronegative as well. Fluorine is the biggest hog on the periodic table. Kind of think of electronegative atoms as hogging the electrons. So one question that's posed here on this page is, why don't the noble gases have electronegativity values? And if you think about what we did on the earlier page, and we drew the electron dot structure of xenon. It's a noble gas, it's in group 8A. There's no space for it to accept or pull in more electrons. So the short of this is they have a full octet. They have all 8 valence electrons that they want, or you can describe it as having a complete valence shell. But once they get to that point, they're not going to pull in any more electrons. It's just not going to happen. There's no place to put them. The opposite of the word electronegative, sometimes you might hear me using this term, so I just want you to be familiar with it, is electropositive. And the electropositive atoms on the periodic table will form cations. They're going to lose electrons because they're not really pulling them in. They're kind of just giving them away. Why do we go into this? Again and again, electronegativity, I always joke around, if you need to take away anything from this course, you need to understand electronegativity, because that enables you to figure out the answers to all sorts of chemistry problems. Why we're bringing it up here though with Lewis dot structures, as we start drawing our Lewis dot structures. So this is the Lewis dot structure for carbon dioxide, the gas that we breathe out when we talk. The least electronegative atom is going to be your middle or your central atom. So if you think about what it means to be electronegative, right? If you're electronegative, you're hogging those electrons. I think of fluorine as kind of being a bully sometimes, right? It's going to take the electrons from everybody else. It doesn't want to share electrons. And you don't want to put like a kid or a bully in the middle of all the other kids, because that's going to create chaos and a disaster, right? They're going to just try to steal from all the other kids. Everyone's going to be crying. So ideally, you would have the person who's best at sharing in the middle. And that's analogous to the least electronegative atom. So those ones that are farther away from fluorine are going to be better at sharing. Carbon is awesome at sharing. Carbon's my like hippie, my tree hugger, just great at sharing. And well, one thing too about carbon is it's not so electropositive that it's a pushover either. Carbon's got the best of both worlds, especially if you look at the value on the lecture handout here. Carbon comes in at 2.5 compared to fluorine's 4.0. So that just makes it a great candidate for a central atom. And again, just don't put fluorine in the middle. That's never going to happen. So in problem 2, we're asked to select the most electronegative of the group. I know you have the values listed there, but in an ideal world, an ideal testing situation, you would just have access to your periodic table, because again, electronegativity is very predictable as long as you remember that fluorine is the most electronegative. So if I'm looking for the most electronegative out of this, I want to pick the element that's closest to fluorine. So here I'm going to pick oxygen because oxygen is super close to fluorine. It's actually the second most electronegative atom on our periodic table. And then of this group, phosphorus is closest to fluorine. So I know that that's the most electronegative. In terms of the least electronegative, we want to pick atoms or elements that are the farthest away from chlorine. So these are all in group 6A, but we want to pick something towards the bottom because that's farther away from fluorine. So here I'll pick tellurium. And then in this set, they're all in the same row, but the potassium, because it's in group 1, all the way on the left-hand side of the periodic table, it's going to be the least electronegative. It's the farthest from fluorine. In question 4, when we're asked to start ordering, the first thing is to make sure we're understanding the prompt. So here they want increasing electronegativity. So that means that we want the least electronegative, and I'll do En, all the way as it increases, then we'll wind up with the most electronegative being the last one on my list here. What I like to do on these, because they could really turn a person around, get a printout of the periodic table and circle all of the atoms that they have, all the elements that they have on your list. So what I did here, I just drew it on the board. So sodium and magnesium and aluminum, silicon and chlorine were all on the list. And it's nice, they're all in the same row or period of the periodic table. They're all in the 3rd row. And as we go across, again, getting closer and closer to fluorine, we expect the electronegativity to increase. So if you had them all circled, you imagine you can see that pattern going across. So I'm going to list them out. The least is sodium. And then the magnesium is a little bit bigger than that. And then we have aluminum, silicon, and chlorine. And so I put sodium is less than magnesium, which is less than aluminum. And sometimes you'll see that kind of notation as well, just to start feeling comfortable with it. Alrighty, so this last problem is probably the most challenging of the group. Here it's critical that you get a copy or a printout of the periodic table and circle all of the elements that they want you to order. As you move up towards fluorine, electronegativity increases. So I'm going to start with radium. Radium's the least electronegative, or it's electropositive. Then I go to strontium, and then next would be gallium, and then phosphorus, sulfur, and then finally fluorine. So you're kind of going stepwise. After you circle everything, you're going to go stepwise towards fluorine. And then let's just write that down. So radium, strontium, gallium, phosphorus, sulfur, and then, of course, we wrap up our list with fluorine. Alrighty, so let's bring some of the discussion together. And here we're going to talk about how we can use electronegativity to analyze the type of bond that we're dealing with. So in an ionic bond, which remember is between a metal and a non-metal, so opposite sides of the periodic table, the electrons are transferred from one atom to another. There's a more formal definition. If the electronegativity value difference, and this is listed at the top of the page there, is greater than 1.9, then they're just not in a position to share. We have someone who wants to give up the electrons, somebody that wants to hog the electrons. No sharing is going on, and so they just transfer those electrons. In a covalent bond, that's a little bit different. Their electronegativity values are a little bit closer. So since they're more similar in character, they're in a position to share those electrons. And we typically see the covalent bonds happen between nonmetals. So stuff on this side of the periodic table. We can subdivide the covalent bonds. So we have two types. We have what's known as a nonpolar covalent bond. And that means the sharing is perfect. An easy example of this to recognize is when you have diatomic elements or diatomic compounds, both oxygens, they're both going to have the same exact value. It doesn't even matter what the value is. It's like twins, right? They're the same age, they have the same kind of personalities maybe, or pretty much the same. So they share very well with one another because their characteristics are the same. So twins are going to have a nonpolar covalent type of relationship, perfect sharing. And then sometimes we have two elements on the periodic table that their values are very close, and so they're going to have near perfect sharing. So carbon and hydrogen also do that. So if you have anything with carbon and hydrogen, so this is CH4. You don't even really have to look at the values. Carbon and hydrogen share really, really well, almost perfectly. So those kind of compounds are going to be nonpolar as well. Over here we have polar covalent. So as the electronegativity values, the difference there gets a little bit bigger, but not extreme enough to be ionic, just a little bit bigger. We still sharing, but the sharing is not equal. So one example here would be between hydrogen and chlorine. What's hydrogen? I think hydrogen comes in at an electronegativity value of around 2.1, and your chlorine is about 3.0. So they're in a position, if we subtract those values, they're in a position where they can share, but since chlorine has a higher electronegativity value, it's going to have the electrons closer. So like this is a bond, we're going to learn about that shortly here. It represents two shared electrons. But it's not going to be like perfect like this because chlorine is a tiny bit of a hog, but nothing too disruptive. So maybe those two electrons are going to be closer to chlorine the majority of the time rather than closer to hydrogen. Alrighty, in this next set of exercises, we're asked to identify the bond types. Definitely you need the values on page 2, or you need another source for electronegativity values. You're not going to just be able to do this by looking at the periodic table. So you need to look up those values. So here we have potassium, which comes in at an electronegativity value of 0.8, and our chlorine is 3.0. So the difference between the two electronegativity values is 2.2. So I'll do delta En, so the difference in electronegativity is 2.2, which means that it's an ionic compound. Remember, whenever you're above, and that's on page 3, they break it down. Whenever you're above a difference of 1.9, you're classified as an ionic compound. The sharing just isn't going to happen. They're too different. We can look up the values, but we don't have to. This is a case of twins. They're going to share perfectly. So we know that it has a difference in the electronegativity values of 0, and this is going to be nonpolar covalent. Perfect sharing between the two hydrogen atoms. All right, continuing on to letter C. So we're going to have to look up some values again. The hydrogen comes in at 2.1, and the fluorine is 4.0. This is a good example. I always wonder about it myself. When I was taking the class, I should have asked. But the change in the electronegativity value here is 1.9. How do we classify it? So at 1.9, you're still considered covalent, but it's going to be polar covalent. So there's going to be sharing, but the sharing is not the best. Fluorine is definitely hogging the shared electrons, though we're not to the point of stealing those electrons, which is what happens in an ionic compound. Sometimes you're asked to analyze compounds that have 3 atoms in there. You don't have to subtract all 3 values because sharing typically happens between just 2 of the atoms, and then the other 2 atoms. Sharing is like on a 1-per-1 basis, if that makes sense. So graph the value for calcium, so 1.0, and then our chlorine again, which is 3.0. So I'm not worried that there's 2 chlorines, I just wrote that number once. And then my difference in the electronegativity values is 2.0. What a good contrasting example. So that 0.1 makes the difference between something being polar covalent and, in this case, ionic, where the sharing just breaks down and we have a transfer of electrons. All right, so continuing with the problems, we look up carbon, and it comes in at 2.5, and oxygen is 3.5. So the difference in their electronegativity values is 1.0, and that makes carbon monoxide a polar covalent molecule. Here we have ammonia. The nitrogen comes in at 3.0, hydrogen at 2.1, and again, another example where we see more than 1 hydrogen, but we just subtracted 1 time for these purposes. So its difference in electronegativity values, 0.9, and we can also classify ammonia as being polar covalent. The last 2 examples are presented as Lewis dot structures. We don't have to analyze both sides, they're very repetitive. So we're going to just take 1 oxygen, which is 3.5, and we're going to subtract 1 hydrogen, which is 2.1. So we get a difference there of 1.4, which makes the water molecule polar covalent. Here we have methane, CH4, but we don't have to worry about 4 hydrogens, we're just going to do 1 of them. Carbon comes in at 2.5, hydrogen 2.1, so we have a difference of 0.4. And so even though they're not exactly the same in terms of their electronegativity value, they're close enough that they're sharing almost perfectly. So when you have molecules of carbon and hydrogen, we can classify them as being nonpolar. It's good to remember carbon and hydrogen form nonpolar bonds because there's so many compounds out there, a lot of biological compounds that consist of carbon and hydrogen. So carbon with hydrogen is going to be nonpolar.